Okay, off to question number 4. One of those problems that is honestly a lot easier to do than it is to explain, but I will do my best to make this nice and clear. So what we have is this little piecewise defined functions. I keep, again, saying it's consisting of 4 line segments. It's actually really kind of an important piece of data. You don't have to assume that it's linear. We actually know that it's linear. That's kind of what all of that's about, is being certain about the shape that you're looking at. Now, when we go on to this whole thing, it says that g is some new function that is based on the integral from 0 to some value of this function. So we have to be a little bit careful because, of course, you know they like to play with those bounds. If x is negative, then it's going to be upside down, and we're going to have to fix that. And you know that they're going to want to do that game at some point in time in here. Now, one of the things that I notice is since g is the integral from 0 to x of f of t dt, then the fundamental theorem of calculus would say then that g prime of x would be f of t, and that g double prime of x would be f prime. I guess it should have said of x here, not of t, because again, the bound here is in fact x. And so this is kind of my setup as I go through all of this stuff. So if I wanted to come up with an interval where g is concave up, now keep in mind, if I want g to be concave up, I need the second derivative to be positive. But the second derivative of this is the first derivative of this. So if I'm looking at f prime being positive, I need every place where the slope of f is in fact positive. And that part appears to happen here and here. And so the answer to part A is actually quite simple, is since g double prime of x equals f prime of x being greater than 0 means concave up, we could say that this happens. I didn't write this in a great place, but this happens on x values being between -4 and -2, as well as values of x between 2 and 6, and we're done. And literally that's all that we needed to say, is that since g double prime is f prime, I needed that to be greater than 0, and we're good to go. Now, for the second part of the question, part B, they're asking us to do a little product rule. So I'm going to go ahead and slide in an extra little piece of paper here. Since p of x is equal to g times f, we're going to start by saying, what is p prime? Well, the product rule says g prime f plus f prime g. Now, I've noticed some other teachers actually write this a little bit backwards to how I do it, but that's kind of how I've always learned to do that. Some people like to say gf prime because they keep the order of those terms consistent. So if we have our setup and now I want to do p prime of 3, then I want g prime of 3 times f of 3 plus f prime of 3 times g of 3. Now, one thing you want to remember is that g prime of 3, according to this thing up here, g prime of 3 is just f of 3. And I can look at the graph and see that f of 3 is right down here at 2.5. No, actually, f of 3 is actually -3. So g of that is 3. F of 3 is also the same thing. As it turns out, those were equivalent, which is a really interesting fact. So we have 9 sitting in the front side. Now, f prime, of course, that is the slope of f at 3. So if we look up here and we find the slope at 3, well, from here to here, it rose 4 and it ran 4, making its slope 1. Now, here's the first place we get into where I'm in a little bit of hot water. I need to figure out what g of 3 is. Well, I need to go to the definition. G of 3, I need to do something off to the side here. G of 3 is the integral from 0 to 3 of f of t dt. Well, let's look at our picture. What is the area under the curve accumulation from 0 to 3? Well, they did something that's kind of interesting. because as you work your way across this thing, from starting at 0 over here to the number 1, I have this little triangle sitting right here, and I could go find that triangle. But as it happens, as I slide across this triangle right here, which I'm coloring in orange just to demonstrate, that perfectly zeroes itself out, because as I accumulate, I actually gained 2, but then I lost 2. So all I really need to do is find this little piece from 2 to 3, and that's the only part that it remains. And actually, they were being very generous by giving you a 1-to-1 grid here. The areas, this is all 1 by 1, so 1, 2, 3.5. So G of 3 is actually negative 3.5, or negative 7/2. So putting it all together, we have 9, which is 18/2, minus 7/2, and I get 11/2, and I'm done with part B. So that was actually not too terrible. So that was part B. So let's check out part C. Now part C asks us about a limit. Now again, being good calculus students, I think you can almost predict in advance that they're going to play with something that we've done a lot of. They love to, at least one place in time, somewhere or other, give you the indeterminate form 0 over 0. Right? So if you see that 0 over 0, we know we're playing L'Hopital's rule games, right? So when you look at that, you could see that we looked at that right here. G of 2 is literally the accumulation of area from 0 to 2, and that's exactly what we saw right here. So this numerator is 0, but as you approach 2, you get 4 minus 4, which is again 0. So this is 0 over 0. So L'Hopital's rule simply says, forget it, let's do it again. Let's apply that limit, but let's take the derivative of the numerator and the denominator and reapply. Well, as the denominator goes to 2, 2 times 2 is 4, 4 minus 2 is 2, and G prime of 2, but we know that G prime is literally the value of f itself at 2. And if we come right here, you can see the value of f at 2 is actually negative 4, and we have finished part C. Give me one more second. And so we've actually finished up part C, and the last part is D. So let's finish up D here. So what is the average rate of change of G on the interval from negative 4 to 2? And does it mean that it guarantees some place? So what I have is, what is the value? Now, again, G of negative 4 actually says to take the integral from, got to be a little bit careful to look back at how that was, 0 to negative 4 of f of t dt, right? That was negative. So we obviously did something a little bit silly, because that means we're going to want to reverse those bounds and go from negative 4 to 0. And we're going to go ahead and put that 0 in front, that minus in front, I should say. And I think that's pretty good. Now, as it turns out, when you do all of that, we can accumulate the area, and what happens is you end up getting negative 16, just FYI. Now, we also said something about G of 2, but we already know that G of 2 was the number 0 because we found that earlier, right? So if you look at the average rate of change of this thing, find the average rate of change of this thing. So we would have negative 16 minus 0 over, I got to be really careful at this thing, about negative 2 minus negative 4 minus 2. So I got negative 16 over negative 6, or in other words, 8/3. That's the value guaranteed by the mean value theorem. And they're asking, is it true that G prime of x will be that f of x somewhere on the curve? Does that guarantee? Well, again, the mean value theorem was actually true for any differentiable and continuous function. But if you look at it, we know that G was differentiable and therefore continuous, because if you look, the derivative of G was f, and since f was everywhere defined, then that means G prime is everywhere defined, and that means that G is a differentiable function and continuous. And by those reasons, what I have right here in my notes is not only do we have that, the mean value theorem says that it must exist because it's a differentiable and continuous function. So we can apply that rule for those reasons. And in your explanation, you actually need to specify that the mean value theorem requires these two pieces. And it is kind of silly because as soon as you have differentiability, this becomes continuous anyway, but you're supposed to say it. So anyway, that's the end of question number 4. All right, see ya.